Hello, good morning everyone. My topic in HVDC systems is the challenges in HVDC systems. What are the challenges we are facing in HVDC systems? We are going to take a look at it. Introduction. Nowadays, the high voltage direct current transmission systems are gaining relevance in long distance and renewable energy integration projects over the conventional alternating current transmission system due to several advantages it has over the AC transmission systems. As the advantages it has are the improved flexibility and independent active and reactive power controllability. Now, by taking a look at this, we will discuss the technical side too. I will tell the definitions for technical also. Flexibility. What is flexibility? It's the ability to adapt to dynamic and changing conditions. Despite that, the high currents and voltage collapses generated by fault conditions in HVDC systems imply some unresolved technical challenges regarding the detection, location, and clearance of faults. Faults have to be cleared in a very short time range in order to minimize their impact, or else the impact may be higher on the system. For this objective, very fast protection algorithms and reliable HVDC circuit breakers are required. However, HVDC grids, similar to high voltage alternating current grids, they are not failure proof. Fault between conductors and ground can happen anytime. During fault conditions in an HVDC grid, two critical situations take place. The voltage drops sharply and the current increases rapidly, which causes the failures in the systems to very high values. When the current increases rapidly to very high values, which is critical in grids with the voltage source converters. The modern HVDC technology, its power electronic devices can withstand only twice its rated current and not the high fault induced currents. If the fault is not cleared very fast, the VAC converter disconnects itself for its self protection. If in this case, the entire HVDC grid can be lost with the corresponding large blackout. Hence, very fast and reliable protection systems are needed in order to avoid damages in the components. This way, a fault must be detected and located and cleared in a very short range of time, which can be defined in the HVDC circuit breakers. Have to be developed and appropriate fault clearing strategy that has been adopted in order to minimize this impact of fault condition in both the DC and AC systems. Circuit breakers. What are circuit breakers? It is an automatically operated electrical switch. It is used to protect the circuit from damage. And the main function of the circuit breaker is to interrupt current flow when a fault is detected. Once the circuit breaker is damaged by a high current or something, it must be replaced. Like it is a one-time use, like a fuse. The topics. What are we going to discuss in this session? Protection requirements, protection systems, voltage measurement devices, current measurement devices, protection algorithms, circuit breakers, the fault clearing strategies that we can do to ensure that we get a more efficient HVDC transmission system. Protection requirements. Fault conditions are dangerous and not only for the system required but also for the people. Therefore, they should be isolated and cleared as fast as possible. Hence, HVDC protection system, it has to ensure the safety and minimize the fault impact and component stress. In order to do so, the protection systems must operate satisfying some performance requirements: accuracy, speed, sensitivity, selectivity, recoverability. These are the some protection requirements that it must follow. Protection systems. The components of a protection system are described. These components are mainly the measurement devices, protection algorithms, circuit breakers, and fault clearing strategies. Measurement devices are in charge of adapting the signals needed by the relays to operate properly. Protection algorithms use these measurements in order to discriminate between the normal and the fault conditions. Circuit breakers isolate the faulty part of the system, thus interrupting the current. They adopt fault clearing strategy determines the impact of a fault condition of a system. Relay. What is a relay? It is an electrically operated switch. It consists of a number of input terminals, a set of operating contact terminals. The switch may have any number of contacts in multiple contact forms like break contacts, etc. The main function. The main function of a relay. It is necessary to control a circuit by an independent low power signal, or several circuits are controlled by a one signal. In this type of uses, we use relay more than other preference of other devices. Measurement devices. The measurement devices adapt the voltage and current signals so protection relays can properly use them. It consists of a primary sensor which adapts the amplitude signal and a merging unit to merge them, which adjusts the low amplitude signal to a suitable format for relays. There are two types of measurement devices to measure signal: current measurement devices and voltage measurement devices. First, voltage measurement device. What is a voltage measurement device? The capacitive compensated resistive voltage divider. A diagram is shown in here in this part. The capacitive compensated resistive voltage divider is shown here. It consists of a resistor and a capacitor that is in a parallel connection. Several RC groups connected in series allow the reduction of the primary voltage amplitude. By this way, the high bandwidth of a few megahertz can be achieved, which will be limited by the resonant effects due to stray inductance in the capacitive part. Optical voltage transformers can also be used to measure the DC voltage. They are based on the Pockel's effect. The voltage and two polarized light waves are applied to an optical medium. The phase shift between two waves at the end of an optical medium is equivalent to the voltage measurement. By this we can measure the voltage. What is resonance? It is a phenomenon in which vibrating system drives another system to oscillate with greater amplitude at some frequencies. This is called as resonance effect. Stray inductances. What is stray inductances? Stray inductance. It is an unwanted inductance in the circuit. It is like any wire or components that have current flowing through them. When current flows through them, it gets energized. It is some unnecessary thing in the circuit. So it is called stray inductances. Previously we saw voltage measurement devices. Now we are going to take a look at current measurement devices. There are different types of measurement devices which adapt the current signal. They are mainly zero flux devices. Zero flux devices means the net flux in the device will be zero. Like positive and negative, which gets cancelled, gives zero. Fiber optic current sensors and hybrid electro-optical transducers. A DC current transformer, it is a zero flux device which consists of two magnetic cores. Two magnetic cores and three windings. Two of these windings measure the flux generated by the direct current, and the remaining winding compensates the flux. Another zero flux device, it is the Hall effect current transformer, which consists of one magnetic core, one winding, and Hall effect sensors. The sensor measures the flux. In this case, the current flowing through the compensated winding is generated by an electronic circuit. In zero flux devices, this current is provided as a voltage through a high burden resistor and is equivalent to the current flowing through the conductor. Their bandwidth can be up to some hundreds of kilohertz. A fiber optic cable wrapped around the conductor constitutes the fiber optic current sensor, which is based on Faraday effect. The speed difference between two polarized light waves is equivalent to current measurement. These waves can travel through the cable in the same direction or different directions. Their bandwidth depends on the fiber optic cable and it is in the range of kilohertz to megahertz. Protection algorithms. The fault conditions must be detected and located in a range of time shorter than 10 milliseconds in HVDC system. As it has been mentioned previously, protection algorithms are in charge of locating and detecting fault conditions. They can be classified into local measurement based or communication based algorithms based on how quick they are. Local measurement based algorithms. It is actually very fast since they use only locally available measurements. However, these algorithms lack selectivity and they are sensitive to misdetection of external faults. Limiting inductors are placed at both ends of the protection zones in order to improve the selectivity of local measurement based algorithm since they damp signals originated outside the protection zone. In addition, these algorithms compare the measurements with threshold values. What is threshold values? We will give a value of threshold in which the values above or below will be taken into account how we give the threshold value as a way of discriminating between internal and external faults. Like if we give a value, if the fault of the current flowing is more than the threshold value, it is an external fault or an internal fault based on the value we give. This threshold value is generally selected through simulations and taking into account that a higher value improves the selectivity but worsens the sensitivity of the algorithm. Some types of local measurement based algorithms are the overcurrent and undervoltage algorithms which make use of the current and voltage. Next, the communication based algorithms. They are based on exchanging data information between both ends of the protection zone. Then, they are inherently selective, but they depend on the communication channel medium and the time delay imposed by it. This communication delay can make the protection system not capable of meeting the requirement of speed. Even if the optical fiber is used, which presents a time delay of 1 millisecond per 200 km. Consequently, the communication time delay is the most limiting parameter in the operation time of a communication based algorithm. Moreover, protection algorithms using a communication channel are not completely reliable since the problem in the communication channel will make the protection system non-operative. Look, here hence they are mostly used as a backup protection systems where the transmission distances are relatively short or to protect against high inductance impedance fault conditions where the speed requirements is not so critical. Improved fault current limiting techniques may enable the use of communication based algorithms as the main protection by limiting the rapid rise of the current and reducing the requirement of speed. The some examples here are differential current algorithm, which compares the current flowing in and out of the protection zone, and the directional current, which compares the direction of the current flowing at both ends of the protection zone. Circuit breakers. HVDC circuit breakers have been commercially available for a short time at very high cost. Due to this, HVDC systems have been traditionally protected from DC faults using AC circuit breakers located at the AC side, since they are a more economical and mature technology. However, they lack operation speed due to mechanical restrictions. Their operation takes several cycles, tens of milliseconds, but in this, the operating speed must be nearly 10 milliseconds, not more than that. So, this is the major challenge in a HVDC system. Moreover, the shutdown of the converter and the consequence of all links connected to it is another challenging issue derived from the use of AC circuit breakers, which is very inconvenient and inappropriate for the case of multi-terminal HVDC grids. Meanwhile, DC protection devices present faster operation. In addition, they allow dividing the grid in protection zones. Like if we have a grid, we can divide it into 3 parts. Hence, fault isolation is achieved while the healthy zones of the system continue operative. If there is a let us assume if there is a fault in between the circuit, like if we have a three parts like 1, 2 and 3. If there is a fault in between the 1 and 3, we can just remove or take out the faulty zone alone and use the both healthy zones. HVDC circuit breakers must offer both operating zone time and high current interruption capability. In addition, they produce a current zero in order to interrupt the current, since it does not cross zero naturally as in AC systems. Moreover, they must be capable of dissipating the energy stored in the system. These functions are achieved using different parallel branches. These branches usually are the main conduction branch, the commutation branch, and the energy absorption branch. The current flows through the main conduction branch during normal operation. However, there will be a fault occurring in between it. The current is forced to the commutation branch in order to be interrupted. The surge arresters located in the energy absorption branch dissipate the energy stored in the system. Limiting inductors. They are used to limit the rise of current during fault conditions to the interrupting capability of the HVDC circuit breakers, in addition to delimiting the borders of the protection zones and improving the selectivity of the algorithm. However, a larger size of the inductor results in the HVDC circuit breakers having to dissipate a larger amount of energy and also affects the stability of the system. Like having a large size inductor will affect the stability. The most common types of HVDC circuit breakers are mechanical, solid state circuit breakers, and hybrid circuit breakers. Mechanical circuit breakers. It presents a mechanical breaker in the main conduction branch, a LC resonance circuit in the commutation branch, and the energy absorption branch. The resonance circuit can be passive. The resonance is triggered by the arc voltage generated by the mechanical circuit breaker opening, or active. Thus, resonance is triggered by a spark gap or a pre-charged capacitor and the semiconductor switch. In addition, they present the highest current interruption capability but are challenging in terms of speed and have an operating time of 5 to 10 milliseconds. Solid state circuit breakers. They consist of a main conduction branch, energy absorption branch, and no commutation branch. The current is directly commutated from the main branch to the absorption branch. Due to this, they present high operation speed and in the order of 1 millisecond, but high on state losses since there is a number of power electronic devices in this branch. Even though they provide greater operation speed, but due to the number of power electronic devices in the main conduction branch, it gets lower. Hybrid circuit breakers. They combine the advantages of the solid state and the mechanical circuit breakers. Fast operation and lower on-state losses. It consists of a number of power electronic devices, very small number of power electronic devices, and a mechanical switch in the main conduction branch. The components of the commutation branch depend on the model. Example: a power electronic breaker or capacitor snubber circuits. The power electronics in the main branch force the current into the commutation branch in order to enable the mechanical switch opening. Then the current is commutated to energy absorption branch, driving the line current into zero. The isolated part of the grid after the detection of a fault condition should be as small as in to order to minimize the fault impact on the healthy zones of the HVDC grid and the AC grid to avoid damage due to stress in the components. In addition, the shutdown of a big zone could affect the AC grid stability. Therefore, impact of fault conditions on the system during the fault clearing and post-fault recovery stages will vary according to the adopted fault clearing strategy. They are classified into non-selective, partially selective, or full selective fault clearing strategies. Non-selective strategy. The entire system is shut down when a fault condition is detected. This is not a good strategy because when there is a fault, the entire system gets shut down, and AC circuit breakers are in charge of doing this. Then the faulty part is isolated using DC switches located at both ends of each zone. Finally, the AC circuit breakers are reclosed in order to energize the system. Fault tolerant converters are usually employed in this strategy. Full selective strategy. This system is divided into different protection zones in order to disconnect only the faulty zones. See, if there are three zones, we can disconnect only the faulty zone and other gets into work like regularly. HVDC circuit breakers are located at both ends of every protection zone. Circuit breakers will be at the ends of both the zones. Like there will be a circuit breaker at the starting of the first and the ending of the second, and the starting of the second to ending of the third, and from starting of the third to ending of the third. Like this, there will be circuit breakers at both the ends of it. This way, the impact of the fault condition is minimized and healthy pods continue operating. This is the most similar strategy to the traditional AC strategy like we use for years. Partially selective strategy. This strategy combines the previous ones. The system is partitioned into several protection zones interconnected by DC links. HVDC circuit breakers or DC to DC converters are placed on the interconnecting links in order to disconnect the faulty zone from the healthy zones after a fault detection. There is no HVDC circuit breakers inside the protection zones. A faulty protection zone is shut down by AC circuit breakers after it has been disconnected from the rest of the grid. Then the faulty part inside the protection zone is isolated using fast DC switches and the healthy pods are again re-energized. Thank you. These are the challenges we face in HVDC systems.